All right, so this is Math317. I have no idea now, maybe lecture 38. I don't know, I'll fill that in later. So we had heard a little bit so far about encryption, about a little bit on RSA encryption, more about elliptic curve encryption. I want to just share a few general items about encryption schemes like this. So one of the things that was mentioned was the discrete log problem, and there's a lot of different ways to formulate it. And I want to just quickly say, what is the standard discrete log problem? How we can solve it very easily in the real setting, but with modular arithmetic, how challenging this becomes. So if I give you, so this is the classic problem. Say I give you, let's do b to the x equals y. Find x given b and y. How would you do this? So everything's a real number. How would you solve this? Yeah, so you get x. So the solution is x is equal to the log base b of y. And of course, we all remember our change of base formula. The log of y base b is the log of y divided by the log of b. And in college, log is always the natural log. And so we actually understand the logarithm function. We have expansions for it. We can just solve a problem like this. The discrete, the mod version is we have b to the x is congruent to y mod some prime p, for example. And we want to find x given b, y, and p. And that's much harder. We don't have a good way to do something like this. That doesn't mean that there isn't a good way. Okay, so just some general stuff about cryptography, and we're going to have another lecture on cryptography. If I start going into too much of what you're going to say, just let me know. The most secure way to communicate is to have two people meet and agree on a secret key. The problem is, to do that, you have to meet and agree on the secret key. And you're not going to be able to do this with everybody you want to communicate. We're not going to have everybody go to Amazon's headquarters. We're not going to have all the secret. So you need ways to deal with things. One way is sometimes you give your different parties code books, and you do what's called a one-time patch. You're only going to use this once and only once. But again, you have to distribute this to all the parties. And there's the danger of this being captured. In World War II, one of the things that really helped the Allies crack the German codes was capturing a couple of code books at times and whatnot. So the question is, can two people agree on a secret in public? And are you going to be covering this, or is this? Yeah.
Yes.
Oh, you're going to, okay, so you're going to cover Diffie Hellman. So you're going to be doing the G to the AB? Okay, good. So okay, so I will not do that if you're going to do that. Okay, so I'm going to skip that. We're going to hear about that on Friday. And there is a way for two people to be yelling in the room, hey, I'm going to do, okay, I'm going to do, and they can say things with everybody overhearing them, and they'll both end up with the secret. It was a major advance when this was discovered. And this is related to the discrete log problem. All right. The next thing I want to comment about is we were looking at y squared is congruent to x cubed plus ax plus b. And we're looking at this, mod some prime. So we have our elliptic curve. It's going to look something like maybe something like this. And if I take 2 points and draw the line connecting them, it's going to hit over here, and then we reflect downward. And so this is P, this is Q, and down here will be P plus Q. And one of the things that we want to do is we want to work with either integers or rational numbers. Computers are very good at working with integers. Rational numbers are just ratios of integers, so that's not going to be a big deal. So let's imagine P is the point x1, y1, Q is x2, y2, and then this is going to be the point x3, y3. And so we have y equals maybe alpha x plus beta is the equation of the line. And so we get alpha x plus beta squared equals x cubed plus ax plus b. And let's assume alpha, I'm sorry, not alpha. Let's assume a, b, x1, and x2 are all rational numbers. So normally we're going to have a and b be integers, so this is not a big deal. And then we're going to assume we take 2 points on the elliptic curve with rational coordinates. We're going to assume P and Q have rational coordinates, okay? Or at least their x coordinates are rational. And I claim that this means that their third coordinate is rational. So not only do we have a way of adding 2 points and getting another point on the elliptic curve, but when we do this, if we started with a rational coordinate for x, we end with a rational coordinate. Well, let's look at, so the claim is x3 is rational. And the proof is we look at x cubed minus ax, so x cubed plus ax plus b minus alpha x plus beta squared. This is going to be a degree 3 polynomial. Can anybody give me a root to this polynomial? So we have this line, and it hits the elliptic curve at P and Q. So if you look at this, you should be able to give me some roots of this. Where is this going to be 0? What value of x will make this 0? X1, because when I put in x1, I've got my y on the elliptic curve for the point P is just going to be x1 cubed plus ax1 plus b, but also on the line, y equals alpha x1 plus beta. So x1 is a root. What else is a root? X2. So I can factor this as this is equal to x minus x1, x minus x2. And then because the leading coefficient is x cubed, is 1x cubed, it's got to be x minus something. Let's call it x minus x3, where x3 is the third root. We know everything in the first line, x cubed plus ax plus b minus alpha x plus beta squared. Everything in that line is rational. If x3 was an irrational number, what would I now know? So this is equal to a polynomial of degree 3 with all coefficients rational. Therefore, x3 is rational. If x1 and x2 are not 0, then it becomes really easy because the constant term is then going to be x1, x2. There's going to be negative x1, x2, x3. And so because that has to be rational, then you know you're golden. If one of x1 or x2 or both of them are 0, then you have to do a little bit more work. But essentially, because it equals a polynomial with rational coefficients, the only way this can be a polynomial with rational coefficients, because x1 and x2 are rational, is that x3 has to be rational. So if you start with 2 rational points, not only do you get a third point on the elliptic curve and only 1 point on the elliptic curve, but that point is also going to have rational coordinates. So this allows us to look at the set of points that have rational coordinates. So this leads to the group, EQ, which is going to be the set of all points xy such that xy are rational and y squared is congruent to x cubed. At this point, I can just do an exact equal, x cubed plus ax plus b. Yes.
For that notation, you're saying your group is E and all elements of E also.
So I'm saying my group is the set of pairs of rational numbers x and y that satisfy the equation. So it's all pairs of rational numbers such that y squared is x cubed plus ax plus b. And it turns out that that's going to form a group. So there are 4 things that have to be true to be a group. The first is closure. You take 2 things in the space and combine them, you get something in the space. Well, that's what this group law does here. The next one is you have to have a zero element. It turns out there's a zero element. It's a little bit hard to see. It's what's called the point at infinity. It's basically just going straight up. The next one is that you have to have an inverse to everything. And then the last one is actually surprisingly hard to prove here. It's associativity, that P plus Q plus R is the same as P plus Q plus R. It can be done by writing down very explicitly formulas for what are the coordinates of sums of points and going through very painful algebra, or there's some tremendously advanced math that you can use to do this. But again, a group is just a generalization of the integers. And it has lots of nice properties. And the idea is you want to come up with some kind of crypto system where it's very easy to do calculations if you know some additional information. And if you don't know that information, it is incredibly challenging and time consuming, and that's going to lead to the security. So the reason this fits into operations research is we need to be able to communicate quickly. If you're planning something like D-Day, which is going to be months of planning, you need a code that's going to be secure for on the order of months to years. If you're in the middle of a battle, you only need your code to maybe be secure for 15 minutes, 20 minutes, maybe an hour tops. After an hour, the information on where your troops are is no longer going to be secret, it's going to be known. So depending on what system you're in, you have a lot of different choices you have to make. Sometimes codes take too long to implement. Well, they may be too long on a battlefield situation, but on the D-Day situation where I can wait months, not a deal. Okay, so this is a good place to stop. We will have our last class and our last presentation on Friday.